I'm excited to introduce the last speaker of this block. This is Amiee Jackson from Oak Ridge National Lab. So her bio reads, following her bachelor's in mechanical engineering at Rochester Institute of Technology, Amiee joined Oak Ridge National Laboratory's manufacturing demonstration facility as a technical professional in 2020. She works on additive processes, design for additive manufacturing, and systems integration. Her experience encompasses material extrusion, powder bed fusion, and directed energy deposition processes with an emphasis on large-scale systems. So we're just going to take a minute to let Amiee get settled, and we will join you right back. Well, thank you so much, Amiee, for presenting today. And yeah, I'll leave the floor to you. Thank you so much.
Thank you. Okay, so thank you all for joining me today. I'm Amiee Jackson, and I'm presenting. I'll be talking about some of the work that a whole slew of folks around my organization have been working on for years, as well as some that I've been working on myself. To make sure that we've got a common framework, I want to quickly describe my organization. I'm at the Manufacturing Demonstration Facility, which is one of the user facilities at Oak Ridge National Laboratory. We're nestled in the hills and ridges of eastern Tennessee, which, if you've never been, is a gorgeous place to be. Now, ORNL's mission, since its beginnings with the Manhattan Project, has been to rapidly transition fundamental science to manufacturing. We're DOE's largest science lab, and it's honestly incredible the breadth of expertise that there is across the lab, including in some core areas like neutrons, high-performance computing, and advanced materials and processes. At the MDF, our mission is to reinvigorate United States manufacturing. We collaborate with lots of different folks from industry and academia, focusing mostly on additive manufacturing to move technologies from low to mid technology readiness level. Now, the MDF is an exciting place to work, in part because of the machines, tools, and systems that we've got around. So here's a little overview. We have over a dozen metal powder bed systems, over 7 large-scale metal-directed energy deposition systems, and more than 4 hybrid systems. Later on, we'll chat a little bit more about a few of these. Now, the landscape of our high bay floor is constantly evolving, so much so that I sometimes joke about being a mouse in one of those constantly changing mazes. Also, a quick plug here. We've got a cool virtual tour on our website if you're interested to dig deeper. Prior to the pandemic, we enjoyed giving tours to visitors and folks all the time, and we hope to someday get back to that. For now, the virtual tour is a great alternative. Today, of ASTM's 7 families of additive, we'll be chatting a bit about the work in binder jetting, directed energy deposition, and powder bed fusion here at the MDF. So let's get started with some binder jetting. Here, we're looking at a demonstration which shows the viability of producing fully dense H13 steels tools for hot work like injection molding. This H13 preform was binder jet printed and then sintered to full density with no infiltration, so this is a single alloy, which is fully dense, and then it was demonstrated on an injection molding setup. Conformal cooling channels incorporated in this design would have been very expensive to create via traditional manufacturing methods. The binder jetting work at the MDF includes metals and ceramics and uses both metal infiltration and single alloy sintering for densification. Another facet to this work in binder jetting is in the digital thread toward creating closed-loop control. Environmental variables and process parameter variables sometimes lead to short spreading of powder, particularly when working with new powder feedstocks. So what we're seeing here is the optical data of short spreading interpreted through the vision software to detect where the part is in green and where there is short spreading in purple. In the graph, we can see the purple line goes up where there is induced short spreading, and then it goes back down as the machine adjusts the hopper settings to compensate for the error. So we can see that one more time. Okay. So there's a lot of potential for binder jetting in many industries because of its high throughput. We're seeing major takeover of the metal injection molding industry, and as sintering technology evolves, we'll see the replacement of investment casting and then traditional tool making. One of the issues that holds binder jetting back is handling the green part before it goes into the furnace. Some of our work is delving into automating the part retrieval, depowdering, and sintering steps to address these process limitations. Imagine creating an archaeologist robot that needs to excavate, clean, and handle these extremely delicate and fragile parts. Sounds like an exciting challenge to me. Speaking of robot arms doing cool stuff, we've got quite a few of those around, particularly in our directed energy deposition portfolio. Here, we've been collaborating with industry partners to create and finesse robot welding systems that produce metal parts by welding layer by layer. The configurations include laser and arc systems. Some use wire and or powder feedstocks, and there are many different kinematic arrangements that enable certain geometric complexities and capabilities. This slide shows a quick sample, but we'll talk a bit more in detail up next. So it all started with MBAM. This system is an absolute unit. One of the original demonstrations was an excavator boom, which was printed from mild steel and demonstrated at a construction equipment trade show. You can see this part in the video of this print. Oh, yeah, there we go. And it's also in this image on the upper right. It's that silver shiny part just before the shovel. More recently, we also built a large watercraft propeller too. Here, we made a foray toward out-of-plane pathing and deposition. Using a robot arm for deposition opens up quite a few interesting avenues geometrically, for example, changing the angle of the deposition vector relative to the starting plane. Exploring these design and process spaces has comprised a lot of the work done here. We've also explored applications in repairing and reworking tooling and other high-value components. So this system framework has proven to be incredibly versatile and high impact. Now, this system has been developed in partnership with GKN, and it's designed for titanium alloys, which are crucial to aerospace applications due to their strength and fatigue properties, but they're also very expensive. The goal here is to reduce the buy-to-fly ratio by printing near-net shapes instead of machining those skeletal structures from large blocks of material. The buy-to-fly ratio refers to the ratio between the amount of billet material purchased and the amount of material in the end part. For some complex geometries, particularly those that have been optimized for lightweighting purposes, this buy-to-fly ratio can be quite high. This ratio can be reduced by printing a billet that is much closer to the end desired part geometry, thereby requiring less machining. This closer geometry is referred to as near net. The booth gets filled with argon while printing to prevent oxidation and porosity development. Our work with this system has led to several cool demonstration pieces, which are enabled by advances in control systems, such as incorporating height control and homing in on optimal processing parameters. Those processing parameters are really key, particularly for different geometries and pathing orientations. An example of the mastery of the processing parameters is some melt pool geometry control work, where secondary geometry was embossed in the printed component that was not part of the toolpath, but rather part of the site-specific parameters. This example is shown in the image on the bottom left, where you can see the Oak Ridge leaf embossed on the part. One of my favorite systems right now is called Medusa. There are 3 welding heads on this system, with each mounted to a robot arm positioned at 120-degree intervals around a large rotary table. Each robot arm moves independently, and throughout a print, an individual robot considers work balancing and collision avoidance in its individual path planning algorithm. This path planning occurs live throughout the print, allowing adaptation and error compensation at any point in time. To make matters more complex, the build table is rotating during the print as well, which has been a fun challenge from the robotics perspective, that is, in planning motion relative to another moving object. As throughput is the most critical feature of an additive technology, this system allows scaling not just in part size and complexity, but also in instantaneous output, which is a high priority avenue of interest. When this system is actually running in the high bay, it sounds a lot like an angry swarm of wasps. Now here at the MDF, our hybrid portfolio is one of our youngest and fastest growing. There are many different definitions of hybrid, but what hybrid means to us is the combination of additive or deposition and subtractive or machining processes in a single system. Hybrid offers the potential for combining the strengths from additive and subtractive processes while also mitigating the weaknesses of each. That is, with hybrid, repeatability, precision, good surface finish, and high productivity are possible, along with geometrical freedom, material options, and less material waste. We've partnered with Mazak in the development of the first serial number of 2 of their machines, one of which is a behemoth with a build volume over 1 meter in length and 300 millimeters in diameter. You can see that system in the image on the bottom left of the slide here. There's a little person for scale. Our other systems utilize blown powder, which opens the design space to multi-material applications as well. Now, this demonstration on the Mazak showed that using the hybrid approach as opposed to additive followed by machining can not only reduce the production time, but also yield better properties in the end because cooling during the machining step can allow for in-situ quenching. As we mentioned the concept of near net earlier, often in additive, machining is required as a post-processing step. Because of this, part designers must consider not just the limitations of the additive processor system, but also tool access and collision avoidance in the machining step. Additionally, aligning and locating an additive part in a separate subtractive machine for post-processing is challenging thanks to the residual stress warping and process anomalies. So hybrid strategies address and simplify both of these challenges. One major challenge that's been identified in hybrid work is toolpath generation and part modeling. Conventional machining workflows typically require a model of the desired geometry and the billet material, and the workflow works unidirectionally in that material is removed quickly at first, followed by refining paths. Typical additive processes require a model of the geometry to print, and depending on the post-processing required, there may be a final part model as well. Hybrid, however, offers the opportunity to add material, then subtract some, then add again, then subtract, so on and so forth ad nauseum. Modeling the part at different stages in this workflow and planning the tool paths required to achieve an in-part geometry quickly becomes complex. As such, our hybrid team has been working with many different software tools to test out and refine varying slicing and path planning algorithms. Here we see a few different slicing and toolpath generation strategies that our hybrid team has developed. For example, in the middle, the chord slicing technique shifts the slicing plane from the conventional orthogonal strategy to slicing planes that are tangential to the geometry, which maintains the width of each layer. Here we can see a few more toolpath generation strategies that have been developed and tested out in conjunction with our hybrid team. On the left, there's a common welding technique called weaving, which is taking place conformally to a curved surface. On the right, we're looking at a spiralization strategy that allows for varying thickness along the wall of a cylindrical part without any stops or starts. Now, our work with electron beam melting was the first additive research program at Oak Ridge. One of the main foci of this research is building the digital thread through in-situ process monitoring. From materials development to system and process improvements, we've been testing and pushing the limits of what can be done with powder bed fusion. On the right here, we're seeing the near-infrared imaging time-lapse of a test artifact build. This is one example of in-situ part modeling for defect detection. Identifying methods for certification so that printed parts can be used in industry is a high priority for our research. To this end, we're gathering and correlating loads of data on each part. Beyond monitoring the printed part, we're also monitoring the machine configuration, the environment, feedstock quality and chemistry, process settings, as well as simulation data to predict the outcome of the print. Then we're rolling all of that information together to make use of it through process property mapping, Born Certified qualification, and the like. We've been developing software tools to make managing and understanding correlations in this data more accessible as well. The figure on the bottom left shows one of our software tools for identifying correlations in this data. One of the most significant outcomes of this work has been that we were the first to control grain structure within additive manufacturing. That was enabled by simulation and all the information from the digital thread. This is a micrograph of an electron beam print where the ability to control grain size was used to spell DOE. Now, how does this work? I'm oversimplifying here, but the main drivers for grain development are heat and time, specifically cooling time. So we can determine what happens where by monitoring and controlling thermal gradients within a part. Where grain structure is fundamental to many material properties such as strengths, conductivities, permeabilities, etc., the ability to design not just on the meso and macro scales, but on the micro scale unleashes all sorts of possibilities for high-impact additive applications. Stick a pin in this idea because we'll circle back here shortly. Up next, we're going to shift gears into one particular application for powder bed, which is electric motors and generators. Now, to set the scene, why motors? Well, motors are kind of a big deal, particularly from an energy consumption perspective. There's ample room for improvement in terms of efficiency, and it really matters. 300 terawatt hours is equivalent to about 35 nuclear power plants, and quad here is short for quadrillion BTU, or 10 to the 15. That's a number that to me as a kid just meant unfathomable. When we're talking quads, we're talking on the scale of world energy supply and demand. Also, motors are everywhere. They're in fans, pumps, compressors, toothbrushes, transportation. They're all over every sector and all around us every day. And the logical converse of a motor, a generator, is critical to our efforts toward electrification and renewable energy sources. So the takeaway is we need to build a system to apply and explore what additive manufacturing has to offer, which would be grain structure control, materials advances, geometric complexity and flexibility. And we need to use that system to improve motor and generator efficiencies and performance within that system. So enter Saturn. Now, a typical powder bed fusion system has a total build volume somewhere around 0.6 meters cubed. But with this current system, we're talking about 0.25 meters cubed. That's about a 4x or 4x, a 400% increase. The system architecture is based in a cylindrical configuration where the build plate rotates. The powder dosing, recoating, and lasers all move in Z. This is a game changer because in conventional systems, these three processes, dosing, recoating, and lasing, happen serially or one after the other. Here, we're parallelizing that, and we've made two sites for this to happen. One of the major limitations to powder bed fusion in general has been process speed, and this system is working to address exactly that. There are several additional challenges to the system, for example, powder handling and recovery, achieving and maintaining an inert environment during printing, and process and toolpath planning, but we're making exciting headway. Now, the fastest powder bed fusion systems on the market today are multi-laser systems that boast build rates up to 120 to 500 cubic centimeters per hour at 42 to 60 cubic centimeters per hour per laser. However, these systems' build rates are limited by their serial process flow. At this point, the recoating step in the process is a constant that may often be more significant than the lasing step. By parallelizing these process steps in a cylindrical configuration on Saturn, we unlock the potential for much higher build rates that are not limited by the recoating time, but rather by the laser speed. Not only that, but this system architecture allows the flexibility for adding more lasing and recoating stations beyond just two for even more process rate gains. You can see in the figure on the bottom right, the target build rate versus future size for this system and systems similar to this would be that red zone. Now, beyond just adding more lasers, we're also exploring how to best leverage multiple beams for microstructure control, as well as guide future system development, such as selection of number of lasers, their power, spot size, beam distribution, and their arrangement. This further expands our capabilities to design microstructures through spatial control of laser power. So there are many soft magnetic alloys used in motors today. One of the most common families are iron silicon. Of the myriad material properties to consider in these materials, three in particular tell a story here: magnetic permeability, electrical resistivity, and ductility. Considering the graph on the right-hand side, we can see that the resistivity there at the bottom generally increases with increasing percent silicon, while permeability is this one with the big peak here in the middle, just at about 6.5% silicon. For the purpose of a motor, higher permeability and higher resistivity are exactly what we're looking for. so that 6.5% is looking like a great choice. The trouble is that the ductility of our iron silicon alloy decreases as the silicon content increases. It actually drops off quite significantly, around just over 3% silicon. In today's typical manufacturing processes, sheets are rolled out and then laminations are stamped from the sheets. So low ductility presents a big problem here, as you can see in this image on the bottom left. Because of this, typically Fe3Si is used in motor components, which compromises on both the permeability and resistivity in favor of the ductility. One of our angles in this research has been to process and use Fe6Si by leveraging the capabilities that AM offers. Some of our research has shown that controlling process parameters and scan path allows for tailoring these properties, and we've demonstrated the ability to print Fe6Si. We're also working on developing Fe6Si alloys that will improve printability further. In terms of magnetic and electrical performance, grain orientation, grain size, and defect density also matter. As we discussed earlier, AM offers the capability to tune and control these. Additionally, by controlling cooling rates, we may be able to retain some mechanical properties and improve processability of 6.5% silicon alloys. Now, some folks who are familiar with motors know that most rotors are made of a stack of thin sheets, and this is done to prevent or mitigate eddy current losses. Some of the work that's going on around here is looking at other geometries that additive enables to accomplish the same goal while potentially offering lightweighting benefits or other potential benefits. Here, the electromagnetic performance of a bunch of different cross-section geometries were compared to see what worked best. This Hilbert filling curve outperformed other designs, and they even compared two different FeSi alloys, the 3% and the 6%, which, surprise, surprise, the 6% had lower power losses than the 3%. So that's promising. Okay, sorry. My work has been our first steps toward printing motor rotors from these electrical steels. What I'm showing here was a first pass for feasibility demonstration, not optimization. So we decided to start small with a simple motor geometry and print these from Fe3Si as an initial point that we can compare to later, sort of like a worst case scenario. In the middle photo, we can see the printed rotors after they were cut off of the build plate via wire EDM, where the one on the left has been treated with a chemical rust remover, the one in the middle hasn't been treated with anything, and the one on the right has been annealed at 1200 degrees C for 4 hours in argon. We observed significant grain growth and formation in the annealed sample, so in the top photo, the large shimmery sparkles visible are actually individual grains at millimeter scale, which is kind of wild to see. In the video at the bottom center, we can see the results of a CT scan of an annealed rotor, which show where the most porosity occurred in the print. Next, we had a local motor repair and rewinding company swap out these commercial laminations for the printed cores, and we tested them. Now, when I briefly tested the rewound motors, I noticed a few key things. First, the printed cores functioned. This may sound silly, but they're a solid core, but because they're solid core rotors and not a stack of laminations, I wasn't exactly sure how bad the losses due to eddy current generation would be. Like, how much heat would that generate? The answer was nothing too noticeable when running them for just a minute or two. The printed rotors did have more losses to noise and required about 13 times more power than the commercial motor at 12 volts. The annealed core required more power than the as printed. This made sense because the annealing process improves the magnetic permeability while reducing the skin depth. Without laminations thinner than that skin depth, or laminations at all in our case, eddy current generation was aggravated. Our next steps here will be in creating printed Fe6Si laminations to compare to these solid printed rotors. We expect to see pretty significant efficiency gains in this next step. We're also looking to apply the lessons we're learning at this smaller scale to large-scale components printed with the Saturn system. Now, this is one example of a potential application that our work on the Saturn system and with these smaller rotors may enable. Most wind turbine generators today are doubly fed induction generators, which offer advantages such as variable speed operation over a range and decoupled control of active versus reactive power. However, one of the limitations of these generators are that they use brushes and slip rings, which result in reliability issues and maintenance. Brushless doubly fed reluctance machines retain these advantages while eliminating the brushes and slip rings. As reluctance machines, they also eliminate the potential for bar skin effect and the requirement for windings on the rotor itself. So other avenues of future work we're excited about include multi-material powder bed fusion, topology optimization of motor design, as well as site-specific grain orientation optimization for motor performance. With that, I'd like to thank you all for your time today, and I'll open the floor for any questions that may have arisen.
Thank you so much, Amy. That was such a fun-filled, action-packed presentation. So many different things there. Again, if you guys have questions, feel free to put it in. There's the chat tab, participants, and then Q&A. So we have a few questions. And the first is probably related to the I'm losing my words here. The robotic printing. Have you done any off-axis printing?
Yeah, we definitely have. We've actually done pretty extensive off-axis printing. For example, the propeller that I showed would be a really good example of that.
Awesome. All right, this is a binder jet question, so I may take it if you want. It says, I've had a lot of challenges with binder jet on shrinking and distortion. What tools do you use to predict how the build part will turn out, digital twins, etc.? I do know that there are some software tools out there to predict shrinkage and distortion that are more or less coming of age. They're being developed. So I think maybe in the next couple of years, we'll see those out and about. Otherwise, there's a lot of work being done on fixturing while you center to ensure that you get critical dimensions met. So, all right. So this is a question about the Saturn system. How would you maintain a reasonable bed temperature with constant lasing?
That's a really good question. I don't know that I'm qualified to answer that, but I would love to get back with you once I've consulted the people who might know.
Yeah, there's a lot of things sometimes that they just work sometimes. And we don't know why, but yeah, I think Amy and her team probably have answers to that you can talk about offline. So it's a good question. And then we only have one more question unless anyone else wants to pop some into the chat. So this question is, I've heard that a major obstacle to hybrid is the need to treat a part after printing and before milling. So I think that means heat treat, thus interrupting the hybrid workflow. How do you deal with this? And I know that you were presenting on hybrid, just as, you know, demonstrating some work that's done at the MVF. So I think this is a good question. I don't know. What do you think? It's I think we're definitely dealing with this, and I think there's some technology around that probably we can't talk about.
Yeah, I know with one of our systems, at least, there's a move to like incorporate some of that treatment in the same system. So it's like hybrid in 3 ways rather than just 2. But I'm honestly not the subject matter expert on that. So I would love to consult with some of our experts and then also get back to you, Michael. Thank you so much for your question.
Awesome. All right. Well, that is all of our questions, unless someone wants to sneak one in. But otherwise, thank you so much, Amy, for presenting on the work at Oak Ridge National Lab. It's always exciting to see those updates. And yeah, thanks again.